about bond boost, a methodology which covers cross-linked polymerization. Actually, bond boost. In this method, the distance between the atoms that are relevant for a reaction of interest can be calculated to determine the orientation of the reactant molecules. So, in some terms, if a suitable configuration is recognized, here we use some additional restraint energy. Most possibly, it will consist of more than one term, which is added to the system that is intended to stretch or compress the bonds at a predefined rate. So, so here today's purpose is that how one second. So here today I'm going to discuss about how this bond boost acceleration method can be used. So for that we are just considering an example of an epoxide and an amine polymerization. Here, so how to set the inputs? So here the two molecules which I'm selecting is one is diglycidyl ether of bisphenol F and diethyl toluidine diamine. So the cross-linking polymerization reaction occurs between the epoxy and the amino groups. So the reaction is depicted in its simplest non-catalyzed form. So these two are my monomers. And so the molecule generation, which is one of the most important step in this process where in the AMS input in the reacts of a panel. So earlier in the previous sessions, we have shown you how to set up the inputs for various methodologies like the same. We need to go to the builder where we have to set the lattice vectors and also we need to upload the monomer files. Basically, it should be an XYZ file or an SDF file. And the rest of the things, the random start, the distance, current density, all are default settings. To, within a single click of this generate molecules, this outcome will come in this 3D interface. So what's actually happening in this methodology? So this is an example, and this is the input creation also, for where we need to create the generation, I mean the region selection. See the terminal carbon. So these are the different steps which I will show you once I navigate the software. So the main, see likewise we need to select all the regions, nitrogens, oxygens and hydrogens. So actually this is the bond boost technology which I would like to discuss here to accelerate a reaction with the bond boost method. So actually, this is the concept that we are going to discuss here today. So you can see in the left-hand side the different inputs which we have given for setting up the process. So in the current reaction, which is depicted here, it will be effective to set atom differences in between the nitrogen and the terminal carbon atom of the epoxide group, as well as the distance between the oxygen atom of the epoxide group, whichever the hydrogen atom of the amine group is closest. So we can see the bond boost methodology, which is stretching and compressing methodologies, which can be visualized here in this diagram. So it is possible to distinguish atoms depending on their chemical environment. For example, a terminal carbon atom of the epoxy group, it will give information provided by the regions to model the reacts occur by the user. So these are the inputs for simulation. So after setting up the inputs for bond boost, we have to give the inputs for the molecular dynamics, where you can see the number of steps and the force field parameters. So this will be the officially the outcome, that how the bond boost is happening and how that specific bond is formed in that specific case. So let me go to the software. So here I'm just going to export. So as we discussed in the last sessions, just to create a directory, just to rename it Bring bond boost only. And then we need to, okay, we need to give the inputs. Hmm. So first we need to select the panel, as we discussed in the previous sessions that how to select the panel. So here it is reactive force fields. So first we need to set the inputs by loading the atoms, molecules. Go to edit, then click builder. So you can see the builder, the lattice vectors. I'm just continuing it with the default settings. And first we need to load the molecules. So there are two types of monomers. First, I'm just adding, I've already downloaded it. So first we need to select this BISF file. So the number of monomer units is 2 because we are just dealing in small polymerization reaction, and then DTD. So these are XYZ files. Just what? So you can see the density, distance, randoms. So I'm just generating the molecules. See, within a single click, you can see the molecule generation is happening. So it is can be visualized like this. So actually, there is no bond in between these molecules. See. So after that, the next step is we need to model the regions. So I'm just closing this tab, and now I'm just going to model the region. So this is one of the most important step in this process. First, I need to select the terminal carbon atom. So I'm just giving the name CT. So now I have to select the terminal carbon atoms. So you can see in the monomer units, there are some terminal carbon atoms. So I'm just selecting it, just press shift. Okay. After that, you just click the add button so that region is selected. So we need to repeat the same step for the remaining regions. So step number 3 and 4. So, same methodology. Okay, and here also shift select. So likewise, we have selected all the terminal carbon atoms. You can see it, the selected portions. So now we have to repeat the steps with suitable nitrogen atoms. So I can see that that portion has been selected. Now we have to go with all nitrogen. So I'm just showing you what are the inputs which you have to give. So the nitrogen atoms should be selected. Okay, the thing is that we need to select the nitrogen. So instead of selecting one by one, there is an option in the selection tab. Just go to select and select atoms of the same type. So it will automatically select wherever the nitrogen atoms are available. You can see nitrogen atoms and just so automatically that nitrogens are selected. And then in the next step, we need to select all oxygen atoms. So the region has been selected and it should be given the name all oxygens. And here, like the same, you have to select an oxygen atom. See the red colored carbonate, red colored representations are all oxygen atoms. Go to select atoms of the same type. So all oxygen atom will be initially selected here and just close. So next we need to select remaining hydrogen atoms. So here, just select a hydrogen and just go to select atoms of same type and then plus just so the all atoms in this. See, we have selected all the atoms. And now the next step is how to do the bond boost. So in here, we have to go to model, the same model tab. And here we need to click the bond boost. So you can see the plus button for the bond boost, just click that button. And then the bond boost lifetime, let's add it as 10,000. And then so plus this detect initial configuration. So this is an important step here in this thing. So here you can see what all things which we have selected, the region. So the region wise selection we have to do terminally. And first we have to select nitrogen, all nitrogens, and then the terminal carbon atoms. And we have to give the Rmax value and R minimum value. So it is 2.5 as per tutorials. I'm just following the same tutorial which we have. Okay. So we need to continue the same for the rest of the regions. So automatically it will display the same and then the terminal carbons to oxygens. And here we need to set it as 1.2 to 3.0. And then we need to arrange for all oxygens and hydrogens. So here the range is minimum should be 3.4 and the maximum is 5.5. So the next step is all nitrogen. And here we need to stop this because the last atom type is said to be one to specify that it must be initially detected nitrogen atoms, that is very close to the terminal carbon atom. So that's why we have given this fifth position to 1. And now the next step is we have set the bond boost settings. So now we have to add the restraints. So this is another important step in this method. So the restraints in the sense means that we need to put the add restraint button, and then we need to select the atoms, choose atoms one. So atom 1, 2. So this that I will tell you once I go to settings 1.5. So this is a parametric settings. It is 0.04. Okay. So for the ERF restraint type, the first parameter, that is this is the PARN1 is the first parameter, is a force constant K. While the second parameter, which means is a maximum allowed force infinity. The maximum allowed force is the most important parameter. It is important to note that when we set the arrangements, I mean these readings, for example, I have given the value zero point 0.5. It is often ripping them apart, while the zero point 0.3 is less than the region which is possible. So the reaction time within zero point 0.2, the reaction takes no longer. That should give more reasonable results in the end. So let me check give the other parameters. So I'm just giving it one by one. So setting it as 4. So here, sorry, I have the wrong parameter. I'm just setting it as 1.5. The same thing here also 1.5. So this parameter is value is effectiveness. And here I'm setting it as 0.3. So again, I'm adding the restraints for the bond boost add-on. So this time I'm giving it 2 and 3. So here we are giving it the Armstrong's 5 and 3. So, okay. So you can see that almost 58 atoms are selected, all these constraints. And now we are going for the execution and visualization. After completing the setup of bond boost, we can test the boost running for molecular dynamics. So just go to the main panel, and then we have to set the task molecular dynamics. So before I proceed for this, okay. So we will give a number of steps, 40,000 for minimum bond boost methodology. So the total angular momentum and angular momentum, everything is given. And then we will go to thermostat. Here I'm selecting Samsung thermostat. I'm just setting the temperature 500 Kelvin and running it for a second. So then, okay. So here I'm just selecting the force fields. So now the force field I have selected. 1 second. So now we have set the inputs and all. We will check it one more time. So why I have selected this thermostat? Because it is the approximate to the correct ensemble, and the approximation is the first for the shorter damping time. So for in this case, generally the crucial part is to set up the damping time as a high practical to still reach the target value in an acceptable time. So especially for this Brunson thermostat, the setting the damping time is too low to known to see the results in severe equipartition artifacts. So the kinetic energy in basically it is transferred from vibrations into rotation degrees of freedom, leading to so-called flying ice cube problem. So this is one of the methodologies which we have undertaken, and now we will go for this. We will save this step. Mm, okay, just a name. Okay, we will. Yeah, file saved, and now we will run it. Okay, so this is the. Okay, you can see the process is running. Any questions? We have set the inputs. Hello, am I audible? So I have set the steps to 40,000. So once this is finished, you can see the dynamics. Any questions regarding the inputs or any method or any steps? So once it is finished, we can see the trajectory. So basically, in this methodology, react needs to be provided to set the atom distance to define a preliminary complex. So if the complex is formed during the dynamics, the external forces are applied to support bond breaking and bond formation, like as to define the sets of bond. So the for the current reaction, we have to set the atom distance between the nitrogen atoms and the terminal carbon atoms of the epoxy group, so which I have already mentioned earlier in the beginning. So the main reactions is between the terminal carbon atom of the epoxy group and the nitrogen atom. So I think that the reaction is about to finish. Yeah. So see, this is the official methodologies which we have taken. And so in the log file, we can see stepwise calculations that what are happened here in the interface. So the dynamics, temperature, potential energy, pressure, volume, and the output. So MD calculations is finished. So just we can go to the output file and you can see the iterations, properties, responsibilities. So the molecular dynamic configuration parameters, what all things which we have set in the inputs, we can be displayed here. The reacts of engine configurations, the force fields, the molecular dynamic parameters, and stepwise calculations. So this is about the overall bond boost method which we have discussed. So any questions? So tomorrow we will arrange a session for question answers. See, this is the output where we can see the MD properties. So the MSB mean square deviation you can set, and also this much properties we can visualize graphically. If we flip this thing, see, you can see how the process is taking place. See, so this is the overall results of our bond boost methodology. So any questions?
Can you please explain again the thermostat part? I mean, why did you choose the Berenson thermostat?
Thermostat, okay, 1 minute. This part, isn't it?
Yes, yes.
Actually, we have this much options, Brunson and NHC. So here in this specific case, we need to correct the ensemble and the approximation from the shorter damping time. So it is in this crucial step, we need to set the damping time as high as practical to reach the target value in the acceptable time. So that's why we have selected this thermostat instead of NHC. For NHC thermostat, the simulation samples the correct ensemble no matter what the damping time to set up, but we recommend to set the damping time which is roughly corresponds to the correlation time of the system. So when we go for this bulk polymerization steps, we need to select this Bunsen thermostat.
Okay, thank you.
So the main thing we have to focus is on how the inputs which we have giving in this specific cases, module wise. That's what we have discussed in the previous 4, 5 sessions. Any other questions? In the meantime, we can see the MD properties. We can, so one by one, we can select the methodologies, kinetic energy, potential energy, volume, density. So these are the different parameters we can refer the number of molecules, volume. So we can represent frame by frame the trajectory and all. Any other questions? Okay, do you try to perform the solutions which atoms are going to be bounded? Yes. And how to choose cutoff? The cutoff which I have already shown you, the same thing, the same methodology. One more time, I will tell you. So in the model, we need to select the regions. So in this specific case, which are the bonds which we are planning to boost? That part we have to select. In this specific case, it is the terminal carbon and the nitrogen. So that was the key, which I have mentioned in the beginning itself while setting that portion. Likewise, if you're doing the polymerization reactions by your own, you should have an idea that which bonds or which atoms should go for that method. So in this typical example, we have selected as per the tutorial nitrogen and terminal carbon. So that's why I have selected these regions. So the region-wise selection is very important for this specific calculation.